Okay, so let's look at 13.3. So if z is a function of x and y, then the first partial derivatives of f with respect to x and y are, so the first one is f subscript of y. This is read the partial derivative of f with respect to x is equal to limit h goes to 0 of f of x plus h comma y minus fxy over h. So this is like a single variable definition of derivative, except the y is the same in both positions here. So the y here is considered like a constant, and the variable here is x for this first derivative. And the second one over here, f subscript of y, this is read the partial derivative of f with respect to y. It looks similar to the one over here, except now the x is constant here and here, and we have the y plus h and the y. Okay, so here we're considering the x a constant, and we're considering the y as a variable on this one. So now let me write some conventions for these. Okay, so again, if z equals f of xy, then so the partial derivative with respect to x, how we define it up here, here's all different ways you can denote that. Okay, so you can be, so this looks like the Math 150, except this has like a curly tail on it. The Math 150 had like a straight line there. Here you have a curl on it, like a delta. So it'd be like the derivative symbol from Math 150, except it's slightly curled up here. So this is read the partial derivative of f with respect to x. So these are all ways you could denote the partial derivative of f with respect to x, and same for y. These are all different ways you could denote it. Okay, so next thing. Okay, so we're going to make a definition f double x down here. So this is the second derivative of f with respect to x. So this is defined to mean the partial derivative of f with respect to x once and then do it again. Okay, then I can define f double y in a similar way. Let me write it here. Okay, so I could define f double y this way. This is the derivative of f with respect to y twice. Okay, so second derivative with respect to y. And then I could have the mixed one. So I could have f subscript xy, that means partial derivative of f with respect to x, and then respect to y. Then I could have f yx also. Let me write it here. So you have y fyx could be defined to be partial derivative with respect to y, and then with respect to x. You could keep going with this definition. You could have f 3x's then and so forth. So you could keep extending this, but we're just going to do the second derivatives here like this. Okay, now let's take a look at an example. Okay, example, this is from practice quiz 4, number 4. It says find the partial derivative respect to x, respect to y, double x, double y, xy, and yx. And here's a function here, x squared ln of x y squared plus sine y plus 2x squared y plus 1. Okay, so let's find partial derivative with respect to x first. So let's write it right here. Okay, so on this first guy here, I'm going to have to use a product rule where the x squared is going to be the first function and the ln of x y squared will be second function. So using product rule, it's going to be derivative of the first function, so derivative of x squared, which is 2x, let me write here. It'll be derivative first, so 2x times second. That's going to be the first, so x squared times derivative of ln. So recall the derivative of ln will be 1 over times the derivative of the inside. So let me write it out here. Okay, so it's going to be first function, so x squared times derivative of ln, so it'll be 1 over, it's 1 over x y squared times the derivative of xy squared with respect to x. So we're treating the y as a constant. So the derivative of x is 1, and there's still a y squared there. So therefore the derivative of xy squared with respect to x would just be y squared. Okay, so this guy is the product rule that I used here. Then moving on to the second one, sine of y. There's no x in this now, and you're treating the y like a constant. So therefore the derivative with respect to x of sine of y would be 0, so you could say plus 0 for this guy. Okay, then moving on to the next one, it'll be derivative with respect to x of 2x squared y. So derivative of x squared is 2x, there's a 2 in front, it's going to become 4xy. And then the 1, derivative of 1 is 0. I can say plus 0 here. Okay, so that's going to be your fx. We can simplify this a bit. So over here, the y squares will drop off, and one of the factors of x will drop off to be an x left here. So let's write what we have then down here. So simplifying, we get then 2x ln x y squared plus x, because it's just an x left here, plus 4xy. Let's box that. Okay, now let's do fy next. So let me write it down over here. Now fy, so we're looking at our f up here. So looking at the first guy, it's not going to require a product rule because you have an x squared, there's no y there. So it's just going to be x squared. Derivative of ln, so it'll be 1 over. This times derivative of the inside with respect to y now. So the derivative of y squared would be 2y, so it'll be 2xy then here. So 2xy. Then derivative of sine of y would be cosine of y. And then derivative of 2x squared y with respect to y would just be 2x squared, because derivative of y would be 1. So it'd be 2x squared, and derivative of 1 is 0. So let's simplify this a bit. So here we can cross an x off and a y. Okay, so let me write out what we get over here then. So we get this, 2x squared over y plus cosine y plus 2x squared. Now let's do f double x next. So for f double x, we'll be looking at fx up here. That's one we'll be taking derivative of, so we're going to be taking derivative of this guy with respect to x. So it's going to require a product rule on this first guy, where the 2x will be the first function, and the ln of xy squared will be second function. So derivative of first function would just be 2. So be 2 ln of xy squared plus first function 2x times derivative of second, so be 1 over xy squared times the derivative of xy squared with respect to x, so just be y squared then, and then derivative of x would be 1, and derivative of 4xy would be 4y. Okay, and let's simplify this a bit. So notice here the y squared crosses off the y squared here, and x crosses off an x here. That's going to be 2 plus 1, so 3. So let me write the answer over here then. Okay, so we get then 2 ln x y squared plus 4y, then plus 2 plus 1, so plus 3 here. Now let's do f double y next. Let me write down here. So my f double y now, I'll be taking derivative of fy, which is this guy, with respect to y again. Okay, so let's first make an observation. This y down here you can bring up and write it as y to the minus 1. Let me do that right here. Okay, so I changed it to y to minus 1 right here. Okay, now we'll be taking derivative of this guy with respect to y. So the derivative of y to the minus 1, you take the minus 1 in front. It's going to become minus 2 x squared. Subtract 1 from 1, so it'll be y to the minus 2. And derivative of cosine to be minus sine of y, and there's no y in this, so therefore the derivative with respect to y would be 0, so just be this right here. Okay, so that's my f double y. Okay, let's do next, say, my f xy. So my fxy, I'll be taking derivative of my fx with respect to y. Here's my fx right here. Okay, so I'm going to be taking derivative now with respect to y. So looking at this guy here, there's no y in the 2x, so therefore there's no product rule required. So it's going to be then 2x times derivative of ln, so it'll be 1 over xy squared times derivative of xy squared with respect to y will be 2xy. Then derivative of x with respect to y would be 0, because it's plus 0. And derivative of 4xy with respect to y would be 4x. Okay, now let's simplify this a bit. So it looks like a factor of x crosses off here, and a factor of y crosses off. So I'm going to write my final answer over here. So final answer is 4x over y plus 4x. You can write this as 4x y to minus 1 if you want. I'm just going to leave it like that for now. And lastly, let's do our fyx. So fyx, we'll be looking at our fy guy and be taking derivative with respect to x. Actually, I'm going to write this as 4x to minus 1 here. So let's do that. Okay, so it changes to y to minus 1. Okay, so now looking at my fy up here, we're taking derivative with respect to x now. So looking at the first one, it's going to be 4x y to the minus 1. Is that over here? Because the derivative of 2x squared would be 4x, and you still have the y to the minus 1. And derivative of cosine to be 0, so be gone. And derivative of 2x squared would be 4x. So that's our answer for this one. And notice these are the same here. And that's no coincidence. Okay, so anyway, we're done with this example. I'm going to write a theorem now. Basically, the theorem says that in most cases, fxy and fyx will be the same. Okay, so we're done with this example. So let me state this theorem now. So I'm going to erase a few things here and state the theorem. Okay, so here's a theorem. We're not going to prove this. So pretty much it says if fxy and fyx are continuous on some open disk, then fxy equals fyx on the disk. So pretty much the fxy and fyx are going to equal in just about all cases. So it'd be very difficult to come up with an example where they will not equal. Okay. So again, we're not going to prove this, so we're done with the section, so I'm going to leave the video here.